as we go across a period, ionization energy increases. All right, ionization energy. Okay, this is going to be cool because it's so tied in with atomic radius. It's just the perfect segue. Ionization energy. And I want to define this for us because, what does it mean necessarily? Ionizing. So this is the energy required to remove an electron from a gaseous atom. So when I write this definition, I am specifically talking about the energy required to remove it from an atom. Now, this is called the first ionization energy when it's a neutral atom and you remove that first one. And we can definitely talk about successive ionization energies. If you remove one electron, then you remove another one and another one. But we'll just start with this initial concept of that, removing that electron. So, for example, if we've got a sodium atom, and if we're doing this experiment and we have some kind of instrument, some research instrument in a lab where we are able to take metals and turn them into the gas phase. So maybe you need to do this with high temperatures and low pressure or something like that. But let's just say someone has done this. And I just explain all that because you might be like, well, wait a minute, sodium? Like, isn't sodium a metal? And isn't a metal a solid? And yes, absolutely. Under standard conditions, it is a solid. But in order to have everything on a level playing field, we need to have them all in the same physical state. So if we're like looking at mercury as a liquid, and then we have argon as a gas, and we have sodium as a solid, then there might be differences in removing an electron that are just based on what phase it's in. And so that's why when we have tables of ionization energies, they're all in the gas phase, so that there's like a level playing field, so to speak. Okay, so the ionization energy then is how much energy for this process to happen, this process that I'm writing down right here. And that is that we've got the neutral atom to start with, and we create a positively charged ion, still in the gas phase, and we have removed an electron. Okay, so this is the process that we're talking about, and we're essentially asking, okay, how much energy was required? I think I'm going off. Yeah, I am. That's okay. Okay. How much energy was required to do this. Okay, this process here. Okay, for sodium, do I have that number handy? I should. I would like to. Hopefully I do. Also do some page turning. $496 kilojoules per mole. 496. Okay. So a kilojoule is a unit of energy. All right. Just like kilocalories or calories are units of energy, kilojoules are also units of energy. And for 1 mole of sodium atoms, you need 496 kilojoules that need to hit a mole of these sodium atoms to eject electrons. Hey, Yummy Rocks, what's up? Nice to have you here. Hello. We're doing chemistry. We're doing ionization energies. All right. So this energy needed to be put in order to essentially kick out that electron. If we were to put in 486, let's say we were 10 kilojoules short, this would not happen. It's not enough. Okay, so there is a threshold that is required in order to make this happen. It's got to be 496. All right. Now, let's say you put in some extra. Let's say you put in 596. You put in 100 extra kilojoules per mole. That electron's still going to be ejected. Okay, so there was enough to make that happen. There is some extra electron, extra energy with that electron. So that electron will take that energy and it will use it as kinetic energy. And it's going to go flying out of there even faster. Okay. So as we talked about on Saturday, we were talking about conservation of energy. 496 kilojoules goes into the potential energy of removing this electron. And I would say, is potential energy fully accounting for it? Is there Coulombic attraction? Okay, so we could argue about what are all the sources of energy, but as chemists, and specifically looking at ionization energy, our main point of concern is how much energy did it take to get that electron out of that sodium atom. And then we are concerned with periodic trends, right? All right, that's what we've been talking about for the last hour and a half, right? So we can then look at this and say, all right, that's sodium. Now let's think about what we know. What have we learned about periodic trends that could help us make some deductions about how the ionization energy will vary as we go from sodium to, let's go across and look at magnesium. Okay? Sodium to magnesium. Let's think about this. Okay. I'm looking to see, as I've been doing for the last hour and a half, I always want to make sure I have numbers handy. Oh, good, I do. Okay. So let's look at our magnesium, okay? What we have learned so far is that we have a trend of effective nuclear charge as you go across a period, right? So as we go from sodium to magnesium, we now have an increase of effective nuclear charge, or in other words, that outermost electron in magnesium, the valence shell, is feeling a stronger pull towards the nucleus in magnesium than it is for sodium. Okay, so if that electron is feeling a stronger pull towards the nucleus in an atom, it will be more difficult to remove that electron. If it's more difficult to remove an electron, it means you've got to put in more energy to make it happen. Okay? So our magnesium, same thing. We are now removing just one electron, but we're removing it from an atom that has a stronger effective nuclear charge, a stronger hold on that electron. So now, how much energy was required to make that happen? All right, stronger hold means more energy, right? So that would be what we would reason. So let's see. I just looked over, got the number, and indeed, 738 kilojoules per mole. Okay, we've got a nice, healthy increase, right? So indeed, our periodic trend for ionization energy as we go across a period ionization energy increases. Okay, why? Due to increasing effective nuclear charge. Increasing effective nuclear charge. So now you can see why earlier I was saying, when in doubt, invoke effective nuclear charge. Okay, that's going to help you a lot in terms of going across a period. Now, in terms of going down a group, we talked about with atomic radius that down a group we saw an increase in the radius due to these additional shells, these additional electron shells. Okay, these atoms get bigger and bigger as you go down, right? So in other words, we are increasing the distance between the electron and the nucleus. And it is a lot harder for a nucleus to hold on to an electron if the electron is already further away. Coulomb's law is something, it is a mathematical formula, but we can talk about it conceptually, that the distance, an increase in distance of two charges is going to result in a weaker attraction. Okay, there's an inverse relationship there. So with that, it means that for our larger potassium, it's got a weaker hold on that outermost electron. That electron's further away. So it will be easier to remove that electron. If we say it's easier, another word for that is it requires less energy. So let's see. Let's look at, and maybe I can squeeze it in here. Let's look at potassium and create that potassium ion by removing one electron. And let's compare the value to 496 from the sodium. Okay. We can fit all this on here. If we're comparing now sodium to potassium, this is the magnesium that we're looking at going across a period. Now we're comparing down a group. Okay. Let me look up that value. Okay. It is 419 kilojoules per mole. Okay, so 496 for sodium, down a group, larger atom, electron further away, weaker attraction to the nucleus, easier to remove that electron, and indeed 419 kilojoules per mole. All right, so our reasoning works. And so down a group, we see ionization energies decrease due to larger atomic radius. And then you can tie in, once you've acknowledged it's a larger radius, then that's an increased distance between the electron and the protons. Okay, you can keep layering on explanations onto that, depending on how detailed your teacher or professor wants you to be in your explanation. So one thing I really want you to keep in mind when you are explaining periodic trends is that you never, please don't explain a trend by invoking the trend. Okay, what do I mean by that? I mean, you don't explain the ionization energy for magnesium is greater than that of sodium because ionization energies increase as you go across a period. No. You have just stated a trend, but you have not explained the trend. The explanation is due to the increasing effective nuclear charge. Okay. The explanation for potassium having a smaller ionization energy than sodium is that potassium is a larger atom. The electrons in the valence shell are further away from the nucleus, and so they are not held as tightly. The explanation is not the ionization energy of potassium is less than that of sodium because the trend is as you go down a group, ionization energies go down. No. Okay, so hopefully I made it clear the difference between those two. What is considered an explanation and what is simply just parroting back a trend, or something you can memorize rather than truly understand.